In the previous class, we studied the binomial theorem for the case the power is a non-negative integer. In addition, we have proved the derivative of 1 plus x to the alpha for x is 1 plus x is a positive and alpha is any arbitrary real number. Its derivative with respect to x was like that. So it is very similar to the integral power whose derivative is nx to the n minus 1. So this is true for even a real number. And actually this is based on the theory of Newton who extended the binomial theorem for a general case. The power alpha is a real number. Okay, and once you know this theorem extended to any real number, then it is very useful in computing various physical quantities appearing in the physics problems. Before we go ahead, we just write down the answer. 1 plus, in case we have a power is n, it is a finite series of x, so it has a 1 according to binomial theorem, and x 2 factorial n minus 1 x squared and so on until the end it becomes x to the n and nx to the n minus 1. The series terminates at x power is n. In case n is a positive real number, positive integer. Once we extend this power to any real number, and to make this series confirm that it is a convergent series, we should choose this one in the region within excluding minus 1, okay, between minus 1 and 1. And we, for safety reason, we exclude the endpoints. Then, as the power increases, this power series expansion becomes smaller and smaller and smaller. Okay, first, we assume that the function, if it is differentiable to nth order and n can be extended to infinity, a function can be expressed as a linear combination of polynomial. For example, if I substitute 0, so f of 0, only the first term survives and remaining piece becomes 0 if I substitute x equals 0. So this series has a function at x equals 0, f of 0. This is nth order derivative. Why don't we take the first order derivative? Then it becomes a first order derivative of x equals and derivative 2 factorial cancels and so on. If I substitute, it is 0, substitute x equals 0, we have trivial identity and remaining pieces all vanish. In a similar manner, nth order derivative can be at x equals 0 can be obtained in exactly as is given. And this is called the Taylor series expansion, and this is true for x equals 0 and for x equals non-zero. this series converges to f of x arbitrarily closely as long as the nth order derivative is known, is calculable to any order. So that is a business of the mathematics. We just assume that the Taylor series expansion converges of f of x, and we compute the Taylor series expansion on the right hand side by taking the derivatives and put x equals 0. And then this function is reproduced by the Taylor series expansion. Why don't we take the derivative of this nth order derivative of whether it is integer or not? Because what we have done is the derivative 1 plus x to the alpha equals alpha 1 plus x to the alpha minus 1 for all real number. Okay? This is what we have proved in the previous class. If I take the nth order derivative, x of k, first order derivative, nth order derivative, so n minus 1, first order, and that is k, x, k minus 1, and dx, n minus 1. So in this manner, I can obtain k, k minus 1, and the derivative is n minus 2, and x to the k minus 2, something like that. And these powers are the same, and this one is greater than n minus 2. This one is n, this is k. So this is, we have difference by 1. And when we reach no derivative, that means this is n minus n. So this is x k minus n. If I substitute n in here, this is k minus 1 equals k minus 2 plus 1. So replace 2 by n, so k minus n plus 1. Therefore, this product begins with k, decreases by 1, and then ends up with k minus n plus 1, and this derivative disappears, n minus n, derivative disappears, and k's power ends with k minus n. Okay, that's it. As a result, nth order derivative is this, and we substitute. Oh, by the way, this is true only for k is greater than or equal to n. If we take too many derivatives, then the original power, then, for example, x squared, we take the derivative twice, that we obtain 2, but if we take the derivative 3 times, it becomes 0. So if we take the derivative too many times, then it becomes 0. What happens if I substitute x equals 0 after taking the derivative? Then what we obtain is, let's see, to have a non-zero, this one should be 0. If it is not 0, if this is negative, the value is 0. If it is positive, if I substitute x equals 0, that vanishes. So the only term that does not vanish is the case when k equals n. So k equals n, it ends up with 1. So k begin with the k, subtract 1 by 1 until the end to obtain 1. So that is k factorial. So nth order derivative of x to the k is k factorial only for the case n equals k, except that everything vanishes. As a result, I can make use of this one to find out the Taylor series expansion. Compute the nth order derivative of this. Okay, so first order derivative, alpha, and power is shifted by alpha minus 1. Nth order derivative, this. By the way, if k is an integer, it terminates at some point at k equals n. If in general, for a real number alpha, for example, 1/2, if I subtract, it never terminates. It is an infinite. So nth order derivative brings in the factor decreasing by 1, and the power decreases, but the factor in general never becomes 0. It has a 0 at some point when alpha is a positive integer. As a result, nth order derivative at x equals 0, as I substitute x 0 for x. The result is I can ignore this identity. This is 1, so we end up with this factor. If it is a positive integer, I can replace this 1 with product of factorials. However, in general, it is impossible to re-express this one as a factorials. It can be expressed as a gamma function that is defined for the real number. As a result, our Taylor series expansion of 1 plus x to the alpha is this kind of form. It is very similar to the expression coming from the binomial theorem for positive integers, but it is an infinite series in general, in case alpha is not a positive positive integer. We can find an explicit example for applying this generalized theorem, a binomial theorem. For example, 1 over square root 1 minus x squared. In the region, we put y equals minus x squared, and power is 1 over square root, so our power is minus 1/2. We copy this result, substitute these values in here. Alpha, alpha, alpha minus 1, alpha, alpha minus 1, alpha minus 2. Divided by 1 factorial, 2 factorial, 3 factorial, and so on. And this used to be x, but we have minus x squared, minus x squared squared, minus x squared cubed, and so on. We can simplify this. Minus minus plus, minus minus plus, so plus, oh, minus 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 minus. So every term in this expansion are all plus. And then we have 1/2, denominator only, 2, 2, 2, 2, 2, 2. Okay, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2. Okay. And then factorials, 2 factorials, 3 factorials, 4 factorials, 5 factorials, and so on. And numerator, 1, 1 here, 1 times 3, 135, 135, and then 1357, 13579, and so on. What are the powers? X squared, x to the fourth, x to the sixth, 8, 10, even powers. So if I compute everything all together, then it becomes this kind of expansion. This infinite series reproduces this expression in the region where x is between -1 and +1. This expansion is quite useful in computing the arcsine integral. So this integral is nothing but the arcsine. So we substitute arcsine 1 subtracted by arcsine -1. Arcsine is an inverse function of sine defined between in this region. So you know sine of x is this kind of form between -1/2 of pi until half of pi. At this we have sine value 1, and here sine value is -1. So arcsine 1 means when sine theta equals 1, it's a theta is half of pi. And because the sine is an odd function, the arcsine is this kind of form. We have y equals x, then this inverse function is of this kind of form. Therefore, this value is it's still an odd function, and we have identical value except for the flipping the sign. Therefore, this integral becomes pi. And this is a kind of way of approximate the value of pi. Another example of binomial theorem extended to real power is this: square root 1 plus x squared. We use the same similar method. Everything is the same except that we have power in here is a plus 1/2. Plus 1/2 alpha, alpha minus 1, alpha, alpha minus 1, alpha minus 2. Denominator 1 factorial, 2 factorial, 3 factorial, and so on. We have plus, minus, plus. This is wrong. This one should be removed. So this is only plus x squared power. As a result, we obtain this kind of formula. And in physics problem, we usually compute the energy of a massive particle moving with the momentum defined in Einstein's special theory of relativity. If the particle is not moving very fast, it's much less than the speed of light, then we can pull this out, and this one becomes mc squared 1 plus p squared over mc squared, and both sides can be divided by mc, and energy divided by rest energy becomes this. And when the speed of light is this momentum is much less than the speed of light multiplied by the rest mass of the particle, then we can make use of this expansion. And what about the first term? First term is 1 plus 1/2 p squared mc squared. If it is very slow, p is m times the velocity. Substitute, then m squared. So 1/2 p squared is mv squared divided by mc squared. What's that? Cancels. And 1/2 v squared over c squared. So energy equals mc squared multiplied by 1/2 c squared v squared. C squared cancel. This 1/2 mv squared. So it's mc squared plus, so we missed this term. So energy is mc squared plus 1/2 mv squared. It's rest energy, and use your kinetic energy in classical mechanics, the Newtonian mechanics.